all day.
Excellent. Right, okay, so in the first lecture, we just talked about vector spaces and function spaces the whole time. So it's probably about time we actually drew some PDEs on the board and started working out how to solve them, which is what we're going to do today. So we're going to start working through the textbook Brenner and Scott today. And Brenner and Scott is quite helpfully organized in such a way that they have a chapter 0. And chapter 0 contains an overview in slightly hand-wavy terms of things that are done in more detail and in more dimensions and for more function spaces and so on later on in the book. So what we're going to do is we're going to go through a chunk of chapter 0, probably not all of it because it also gives overviews of bits of the textbook that we probably won't even bother to cover in this course. But we'll go through the first chunk of chapter 0 and attempt to get an impression of how the finite element method works mathematically, why the finite element method produces something which you can argue is a solution in some sense to your partial differential equation, a little bit about why that solution is accurate, and some other properties like that. And we might get up to a little bit of an overview of how the implementation works by the end of the second part of the lecture. So that's the theory for today. There is a slight warning here. So mathematics is plagued by the fact that every mathematician has his own notation. And the sufficiently pedantic of you may notice that the notation in Brenner and Scott is ever so slightly different from the notation I used yesterday. So they seem to prefer to use round brackets to angle brackets for inner products, and they seem to think that the 2 and L2 is a superscript instead of a subscript. Hopefully nobody is going to be too confused by that. So, why do we do the finite element method? We do the finite element method to get approximate solutions to partial differential equations. So we need a partial differential equation, and we're going to make our life easy, and particularly my life easy on the board. Today we're only going to look at one-dimensional cases, and we're going to look at the classical second-order linear problem, because it's the one that has the nicest properties in the finite element method. In fact, it's so associated with the finite element method that occasionally people who are not finite element people who work in finite volume land and so on, will vehemently tell you that the finite element method is a method which can only be used to solve this problem. And we will later in the course see that that is in no way true, but it is the classical one for this problem, so we'll do that. So the problem that we will attempt to solve is minus the second derivative of u with respect to some independent variable, which we will call x, is equal to f. So what does this mean? So f is some function which we assume we know on a interval, and so we're actually going to have this on the interval 0, 1. So it's just a one-dimensional interval. And later on we'll start to get concerned about what function spaces these things might need to come from, but at the moment it's just a function. And so what this is saying is there is some function u which I don't know, whose second derivative with a minus sign out at the front of it is equal to f. And this is not a course on PDEs. If you want a course on PDEs, there are many excellent ones around the college. But if you do a course on PDEs, you will know that this is not actually sufficient to uniquely specify a solution. In order to uniquely specify this solution, we need to say something about boundaries. And in order to make this slightly general, we're going to put a different boundary condition on the left to on the right so that we can see how the finite element method can deal with different sorts of boundary conditions. So on the left, we're going to put a Dirichlet condition, which means we're going to say what the value of the function is. So we are specifying in advance that this function will be 0 at the left-hand end, and at the right-hand end we're going to specify a Neumann condition. So Neumann condition means that the derivative, and all the way through here, Brenner and Scott mix this notation for derivatives with this notation for derivatives, and I'm going to do the same thing as well. I'm going to use whichever one seems to be convenient from time to time. It means exactly the same thing for current purposes. So the derivative of u evaluated at 1 is also going to be 0. So that's saying that at the right-hand side of the interval, we don't yet know what the value of the solution will be, but it will be flat in some sense. So I am not going to, in any sense, enter the theory of partial differential equations in this lecture, or probably in fact in this course. You can either know already that that is a well-posed problem which has solutions, or you can believe me, or you can not believe me, but I'm not going to spend my time proving it. So, last time we spent quite a lot of time talking about function spaces, and in particular we spent quite a long time talking about the L2 inner products and L2 as a function space. And so unsurprisingly, the reason we did that was because it's going to be the place in which we do a lot of the solution of our equations. And so the first step in the finite element method is to turn this strong equation, so this equation that applies pointwise to this function, into an integral equation. And the way we do this is by multiplying by a suitable test function, and once again I'm waving over for just about 3 lines what suitable might mean in this context. I'm going to multiply by a suitable test function v and integrate over the domain and integrate by parts. So it's convenient to move f over to the left hand side at this point because we're going to do all our manipulations on the right hand side. So I'll follow the notation and say inner product of f and v. So in this context that means the L2 inner product. So that means the integral of f times v over the domain is equal to, now we could just write out the inner product here as well, but we'll write out the integral and then we'll show the manipulations we're doing to it. So that's just multiplying by v and integrating over the domain. For reasons that will become more apparent as we go on, we would prefer to have this in a form where we didn't have a second derivative here. And in particular, taking that second derivative out is also going to help us with the boundary conditions. So if I integrate that by parts, I'll get the integral from 0 to 1 of the first derivative of u at x plus times the first derivative of v at x dx. And of course, if I integrate by parts, I also get boundary terms, and boundary terms in one dimension turn out to be the evaluation at the end of the interval. So that will be u prime of x times v of x at 0 and 1. And because I started with a minus sign, this thing's going to have a minus sign, that thing gets a plus sign. It's going to turn out not to matter, because I was very careful in choosing my boundary conditions to make my life exceptionally easy at this point. So let's do the right hand end first. So when we evaluate u prime of x times v of x at 1, well, we know that u prime of x at 1 is 0. So the right hand version of this term just goes away. You can just cross it off. At the left hand side, that's not necessarily true immediately, because I know what u is at the left hand side, and I don't yet know what u prime is. And so the solution to this is that I make a choice about which function spaces I'm going to be in. I make a choice of the function space so that the function space itself satisfies the boundary conditions. So I'm going to choose for my function space here, the space v, and v is going to be equal to the set of things in L2. So if you remember from last week, and I'll attempt to remember to use their notation for L2 in here. So this is the space of all functions on the interval 0, 1, whose square integral, so if you square it and take the integral over there, is a actual finite value. So that's a huge class of functions at the moment. We're going to have to get a bit stricter than that. And I'm going to apply another constraint, which is the boundary condition. So that is that the function at 0 is equal to 0. So that's how we're going to impose the boundary condition here. All functions in this function space have to satisfy the boundary condition. And I also need this equation to make sense, right? So there's no point in looking for functions for which this term doesn't work. And so the way we do that is we also require that this operator is finite, so it has a real value which is not infinite on the domain. And so the way we notate that is we write that A of u and v is equal to this term here, integral from 0 to 1 of u prime of x, v prime of x dx. And so in our function space specification here, we specify that AVV, which turns out to be sufficient, is a finite number, is less than infinity, exists, happens. So what we've done is we've restricted ourselves to a set of functions where the operators in the differential equation make sense and the boundary conditions are satisfied.
Can I ask what the equal sign colon means? In their
it
notation.
means defined to be equal to.
Okay.
So in maths we use the equal sign operator to mean a whole bunch of different things, which is slightly inconvenient.
I'm used to it being 3, I guess.
So no, that's different
Okay.
as well. But, so in this case, yeah, it's defined to be equal to is colon equals. Yeah.
So why did we need a test function v?
Okay. The short answer is I want you to suspend disbelief about why we did that until we prove the other end. So this is how maths normally works. We do some things which don't seem to make any sense whatsoever, and then we come back and we discover that they have the property, exactly the properties we needed.
And by AVV, what do you mean, sorry? AVV?
Okay, I just defined it.
Oh,
yeah.
that thing, okay.
Okay, and so if I now forget my first line, I've lost my border eraser here, which is slightly inconvenient. Oh, right. So let's forget our first problem. So we can now give a specification for our problem. So what we want to do is find some function u in V such that A u v equals f v for all v in V. So that is the variational or weak form of the problem. So those are two technical terms. And so all I've written down is this statement again. I've just written it down specifying now where I want my functions to come from. So we call this a variational form because it is the form of the equation in which V is allowed to vary over all possible values. That's the terminology there. And as we'll see as we go through this lecture and through the course, we call it the weak form because it is a weaker constraint on what the solutions can be than the strong form of the equation. So there are solutions to this which are not solutions to the original differential equation. And that's kind of why we did it, because ultimately, when we do the finite element method, we normally have C0 functions, right? We normally have functions which are not differentiable everywhere. They're not differentiable on the edges of elements. And generally, we wouldn't expect those to solve an equation that depended on taking the derivative of those functions. So we really want to be able to find something that we can call a solution to this differential equation, which isn't actually a pointwise solution everywhere. And that's the game that we're attempting to play. And it's also going to be the case, as we'll see quite soon, that in fact in doing this what we've done is to find yet another inner product. So this thing is actually an inner product. It has all the right properties. And that's going to be very useful in proving things to do with the conversions. I've also played very, very fast and loose here with the concept of what counts as a derivative. And for the purposes of this lecture, I'm just going to let that hang. So I'm going to say, well, I can take that derivative on the interior of the domain, on the interior of every element, so I can take it everywhere where I need to. And in a future lecture, we will come back and make slightly more precise the concept of what it means to actually take a derivative in those senses. So, I've made one big claim about this, which is that there are solutions to this which are not solutions to the original equation. We'd actually like to be able to say something the other way around, right? So now that we've turned the equation into this form, and made some statements about the function spaces we're in, we'd like to kind of be able to claim that solutions to this, or at least some solutions to this, have something to do with solutions to the original problem. We'd like to make sure we haven't thrown out the baby with the bathwater and we've ended up with something which is still in some sense our original equation. And the answer is that if the functions we use here are sufficiently well behaved, then the solutions to this are solutions to the original pointwise equation. And what sufficiently well behaved means is we need f to be continuous, so f in C0 of 0, 1, I'm going to leave off the 0, 1s here just to lose some blackboard clutter. We need u in C2. So C0 is the space of continuous functions, C1 is the space of functions which have a derivative which is continuous, C2 is the space of functions with two continuous derivatives. And so this is a sort of unsurprising constraint, because remember our original equation has a second derivative of u in it, so it's sort of unsurprising that we have a requirement that we can take a second derivative of u. And so the theorem that's written in the notes is if we have this, then solutions to this are pointwise solutions to our original equation. And the way that we can do this is we can say, okay, let's choose. So now remember that these solutions are solutions for all v in our space V, which is a very big space, which is a space that contains lots and lots of functions. The big trick that you will see come up again and again and again for proving just about anything in the finite element method is to choose the right test function. So because this has to be true for all test functions, at any point in almost any proof, I can make a choice about which function I'm going to test with, and the statement still has to be true, because it's got to be true for all. And so what I'm going to do in this case is I am going to need to integrate this by parts back to get back to the original version. And when but just to be able to write this out in the strong form, I'm going to choose those test functions v which are at least differentiable. So we'll choose functions v from this space which are also C1. And it's pretty obvious that all the C1 functions are in, sorry, not all the C1 functions are in there. All the C1 functions are that are interesting are in L2. We've got an additional constraint here, which is that things have a finite integral of the product of their derivative with themselves, while actually the C1 functions are quite well behaved in that regard as well. So it's sort of clear that those functions do exist. And so what we do is we say, okay, let's take this one back. The integral of f times v, that's equal to a uv, which is equal to the integral from 0 to 1. So we're going to integrate by parts back again of minus u prime prime v dx plus. Okay, so then the same trick applies. So we have u prime v at 0 and 1, and u prime, and at 0, then we already know that's 0 because of the function space we're in. So we end up here with u prime 1 v1, this time with a plus here because of the way round that we're going. So now what we can say is that the linearity of these integrals, or the inner product if you prefer, cuts in. So I can rearrange. So I get that f minus u prime prime v equals 0 if for all the functions such that if v at 1 equals 0. So there's a big if there.
So is that
Sorry, why?
the penultimate line? Is that second term on the right hand side not just 0 because you joined the boundary?
You prime.
No, because I haven't proven that yet.
Oh right.
Right? I need to prove that this satisfies the boundary conditions. So I've got a solution u
But
to
you
the
haven't
weak
yet.
one.
Yeah,
I'm
yeah.
trying to prove that that is a solution to the strong one. So I'm definitely not allowed to assume that it's a solution to the strong problem and therefore satisfies the strong boundary condition, right? That's technically known as begging the question. So the next step here, they've got rather technical about, but actually we don't need to get that technical, it's rather straightforward. So one of the things is, so if we assume that v1 is 0 here, this statement here implies that f is equal to u prime prime. So that would not necessarily be true in the L2 norm, right? Because they could differ at individual points. But because f and u prime prime are both continuous, so that's a statement about continuity, and that's a much stronger statement than continuity. If they differ at any point, they must differ on some interval. And if they differ on some interval, then this integral is not going to be 0. Right? So in particular, I can choose v to be a nice continuous function which is non-zero everywhere in the interior of the domain and positive, so nothing cancels. And that being non-zero will then cause us to be in trouble.
So is it obvious why this second inner product is 0 if e1 is 0?
So I've just moved this over to here. So this statement is the same as this statement. Right? Just by linearity of the inner product. So once that's true, then if this thing is non-zero anywhere, it's non-zero in some interval, and I can choose v to pick out that interval and give me a non-zero value. So that's the proof that this is true. In the notes, they actually give you a particular case of a test function you can find. I think that's a little bit overly pedantic. So we know, therefore, that minus u prime prime equals f, subject to that constraint over there. Now we can go back to this statement again. And we can choose the function v of x equal to x. So let's do that. If I put my eraser again. Trying to erase things off so that we don't go too far down. So that says that. So the function v of f equals x is clearly in our space because the function x at 0 takes the value 0, and it's C1, and in fact it's C infinity, and beautifully well behaved, and so it's clearly a function we're allowed to use at this point. That's equal to that's equal to okay, so that's just a substitution. Now, we know that everywhere in the interior f is equal to u prime prime, right? It's true except at this possibly at this one point, which we don't have to worry about.
Isn't that x a 1? You prime
Yes,
1.
that is a 1.
Yeah.
Right, the function x is valued at 1. So in the interior we know that this equality holds. So those integrals have to cancel. And so what that's shown is that u prime 1 times x at 1 is equal to 0. So x at 1 is 1, so u prime 1 is equal to 0. So that's the boundary condition. So it is true that if I can do enough calculus, if I can do enough differentials of the functions I plug in, then I get back to where I started. If I didn't require that you could take these derivatives, then I wouldn't have been able to take these steps, right? So integration by parts only works if all the functions concerned are differentiable enough. And so that was an actual requirement. I would have got in trouble if I hadn't had that requirement. I would not have got back to the beginning. So there's a comment now in the notes which is quite useful to talk about some of the nomenclature. And some of the nomenclature about boundary conditions gets quite confusing in these terms. So in straight PDE theory, before we started talking about weak forms, and definitely before we start talking about discretizing anything, then we have names for different sorts of boundary conditions. So a boundary condition where I set the value of the solution is called a Dirichlet condition. And the boundary condition where I set the gradient of the solution is called a Neumann condition. And there are Robin conditions and Sommerfeld conditions, which are combinations of the above. In finite element land, a Dirichlet condition is quite often called an essential boundary condition. Not because it's essential that you comply with it, but because it's in the essence of the solution. So because we've changed the solution space to have those boundary conditions, they're known as essential. And the Neumann conditions are quite often called natural conditions, and in a sense they're called the natural conditions because they naturally fall out of the problem. Just cross off integrals or substitute integrals of values and they fall out. These are terms which come from the elliptic operator history of the finite element method. So it comes from solving this sort of equation. If you are solving other equations, you may well find yourself in a position where you get a natural boundary condition which is in fact Dirichlet and vice versa. So that's quite a confusing setup, but at least while we're doing these conditions. And a terminology that is used a lot around here on the Fluidity project and on the Phaedric project are weak and strong boundary conditions, which is a more ambiguous term. So a strong boundary condition is an essential boundary condition. It's a boundary condition which you impose by changing the function space. And a weak boundary condition is a condition that you impose by having an integral on the surface. So that's like a natural boundary condition in this terminology. So there you go. You've got 3 different names for each sort of boundary condition, just to cause you lots of confusion. So, moving forward, at the moment we haven't done anything discrete at all. At the moment we've just proven that if I write a differential equation in integral form then the solution to that can have something to do with the original differential equation. So far that wasn't amazingly useful to us in computational science because it's still an infinite dimensional solution in an infinite dimensional function space, and my computer can't handle that. So this is where the next part of our lecture last week comes into play, because we just proved various things and manipulated various things for lots of functions. And a lot of those things are going to keep being true if we choose a subspace of the function space. So the next trick is to choose a finite dimensional subspace of the function space we're in, and then do some of the same things. And it actually turns out to be fairly magically true that just by choosing a finite dimensional subspace of the function space, we get a numerical method, and it just falls out. That's the beauty of the finite element method, particularly in comparison with its competitors. So we're going to keep following their notes. So we're going to assume we've got S, which is a subset of V. And in fact, we're going to say it's more than a subset. We're going to say that it's a subspace. And we're going to, for our purposes, assume that the subspace is finite dimensional, because it's not really very interesting to us if it's not. And so what we do is we go back to our variational problem, and we now say we're going to look for US in S such that A US V equals F V, I can't write, for all V in S. So I've changed two things. Said I'm only interested in solutions in US, which is, in some senses, making my life harder, because I've excluded a whole bunch of possible solutions. But I've also said I'm only going to test with test functions V also in the same space, which in some sense is making my life easier, because I now don't have to satisfy the equation with respect to almost all the functions in this space. And this turns out to already define a discrete system. So that is in fact the discrete system you're going to solve, assuming you know what S is, right? Assuming you've made a decision about which function space S is in. And in fact, in order to practically solve it, you need to make a choice about a basis for S as well. And we're going to do that in the rest of this session. And so the big surprise stepping forward is we can actually solve this. And so if we have F in L2, 0, 1. Whoa, what did I do there? Suddenly, I'm allowing F to be in a vastly bigger space. I don't need F to be continuous. I need very, very little restrictions on F whatsoever. I just need it to be well behaved in our inner products. Then this has a unique solution. So then, in some sense, my method works. I can at least solve it, and I get a unique answer. And the way we do this is, well, as I said, in order to actually practically do anything, we need to have a basis for this subspace. And so we're going to choose a basis. And at this point, we don't really care very much which basis it is. So I choose the basis phi I 1 less than or equal to I less than or equal to n. So n is the dimension of the subspace. It's the number of basis functions which is required. And what that means is that I can write US as a sum of uj phi j. So this means that I have n unknowns for u, which are multiplied by the phi basis functions. So this is an unknown vector n long of coefficients that go in there. And the next thing I can do is I can write Kij is equal to A pi j phi I. So what's that saying? So that's saying that if I choose my basis functions and drop them into my original integral, so the integral of the derivative of that times the derivative of that, then for each pair of basis functions I get a number. And so there are two dimensions of variability there. So that's a matrix. It's a matrix of the integrals of all the combinations of basis functions in my system. And I'm going to do exactly the same thing to f. So I'm going to get, I'm going to write fi to be the inner product of f with phi I. So now I have a n-long vector of f's, but this one I know, right? So I don't know the value of u, so this is a vector of unknowns, but I do know the value of f, so I can calculate what all the fi's are. So what that means is, if we go back to how this was written, then K U equals F is the same as this system if I just test with the basis functions. So if I choose a set of basis functions to be a list of n test functions, then I get a set of n equations, one equation per test function. And so what would be in that in that equation on the right-hand side, that's the easy one, it would be the integral of f with that test function, and that's what I've said is the ith entry in f. So that's what's going on there. Then on the left-hand side, I would have A of u, all of u, tested with phi I. But A is linear. So because A is linear, I can put the phi j's inside and pull the coefficients outside. That's what linearity means. And so therefore I have here k times u. So if you multiply k times u, then that's just a number on each row as well. So that's the set of equations. And it's a set of equations which is equivalent to this if I choose the basis functions to be just, the test functions to be just the basis functions. Now, why did I choose the basis functions to be just the test functions? And the reason I did that is because that's sufficient. The reason it's sufficient is, suppose I take any function out here I like that's in this subspace S. Well, any function I like, v, is equal to vi phi I. Right? That's what it means to be in this space. So now I can split up this statement, because it's linear here and linear here, into a sum of vi outside of this expression times these terms with phi I in them, which are the terms that I know. And if the equation was true for all of those terms, then that would just end up to whatever these numbers were times 0 in every case. And so it's sufficient always to test with the basis function. If you test with the basis functions, then you know you've tested with all the solutions, all the equations in the function space. Yeah.
Can I ask what big U is there?
Define
It's
here.
US, right?
No. It's the coefficients here.
Right. Okay.
So that means I have a system of a finite number of linear equations. It's a matrix equation. And phi I goes from 1 to n, phi j goes from 1 to n. So this is a square matrix. So I've got some hope that I might actually be able to solve this thing. And in fact, so uniqueness and existence are the same thing for a finite dimensional system, right? So if you have a matrix system, then if it's a square system, then the uniqueness and existence come out to the same thing. Those are the possibilities for whether or not you can solve systems. So the problem would be the case then, what happens if there are multiple solutions for to the system? So multiple solutions means that somewhere out there there's a non-zero vector such that kb equals 0. That's what it means to have multiple solutions to a matrix equation, because matrix equations are linear, so everything inside is well behaved. So is that true? So if we write, so given this non-zero v, we can write v to be equal to vj phi j. So what that's saying is, given this vector, I can recover the function that corresponds to that vector. And what we then know is if kb equals 0, that's saying that a v phi j equals 0 for any phi j. So what we can then do is, because this operator is equivalent to this operator, that's what we just showed. So these are the same.
Shouldn't that be a sum in the middle, or is it in vector notation?
That's a sum.
Oh, okay, it's an Einstein notation.
Yep,
Okay,
two repeated indices, it's a sum. Yep. And so that's a vector, right?
Yeah.
So, and so now we can take so now we can take this and multiply by Vj again. So what we get is A V V must be equal to 0. That's a requirement. So now let's go back and remember what this thing originally was. This thing's originally an integral, right? It's the integral from 0 to 1 of v prime x. Well, now it's v prime x, right? So that's just v prime x squared dx. And if we get to this point, then if we're prepared to assume that our functions are sufficiently nice, and remember, our functions have a certain amount of differentiability. We haven't, so I am explicitly hand-waving a little bit here because we need to define certain things about the function spaces that we're not going to do today in order to do this. But assuming that that's a slightly nice function, then that thing is only going to be 0 if v prime of x is 0. Right? And so this can only be true if all these are 0. So that means that there isn't a non-zero v such that kv equals 0. And so that's sufficient in linear algebra terms to know that this thing has unique solutions. And because this is exactly equivalent to that proves that in our discrete space we get solutions. Okay, I think we should stop for a quick break now because I think we're probably at least at the point where people need it. Yes. So we'll stop there briefly.